Hi everybody, welcome to Lecture 4 of Electrical Engineering 331. In this lecture, we are pretty much finishing up Chapter 1 in your book. We will be looking at the impulse function and also energy and power signals. We may still do some problems from Chapter 1 in future tests, but we will be moving on to Chapter 2 extremely soon. In fact, probably in the next lecture. So the first example I would like to look at today is problem 129A, which says to use the sampling property of impulses to compute the integral from negative infinity to infinity of t cubed delta of 3t minus 6 dt. Now, I'll leave it to you to read in your book about the details of the impulse function. The most important property is the sampling property, and so we're going to see how that works right now. So we want the argument of the delta function to be just t or just u, just a single parameter. And that's not the case here. We instead have 3t minus 6. So what we will do in order to evaluate this integral is we will introduce a new parameter u, which is equal to 3t minus 6. Well, if u is equal to 3t minus 6, then we can take the differential of both sides, and we get 3u is equal to 3 dt, which of course means that dt is equal to du over 3. So now we're ready to rewrite this integral in terms of this new parameter u. Now notice that when t is equal to negative infinity, since u is equal to 3t minus 6, then when t is negative infinity, u will be negative infinity. So the lower limit on the integral stays at negative infinity, and by the same reasoning, the upper limit stays at positive infinity. Now, since u is equal to 3t minus 6, that means that t is u plus 6 over 3. And so we're going to substitute that for t. And it's getting cubed. And then the delta of 3t minus 6 becomes delta of u, and then dt becomes du over 3. Now that we have the integral written with the delta function having a single parameter as its argument, what we do is the following. We ask ourselves first if u equals 0 falls in the range of integration, and it does. And so then the integral is simply equal to everything here in the integrand except for the delta function, and all that stuff should be evaluated at u equals 0. So we would have 0 plus 6 over 3, which is 2 cubed. So then we have 0 plus 6 over 3 cubed. And then we don't want to forget this 1/3 out here. So we have 0 plus 6 over 3, which is 2 cubed, so that's 8 times 1/3, or 8/3. And it's just that simple. That's how we use the impulse or the delta function. Let's look at another example. In problem 128C, again, the argument of the delta function is not a single parameter. And so we will again introduce a change of variable, and this time again I'll call it u, but this time we'll let u equal t plus 2. And if we take the differential on each side, we get du is equal to dt. Now let's be careful with these limits. When t is equal to negative 3, remember u is equal to t plus 2. When t is equal to -3, u will be -1. So the lower limit on the integral becomes -1. On the other hand, when t is equal to -1, the upper limit, -1, then u will be -1 plus 2, or +1. So that's why the upper limit on the integral is now +1. Okay, if u is equal to t plus 2, then t is u minus 2. So we substitute in u minus 2 for t here. And we bring down this exponent of 5. And now the t plus 2 in the argument of the delta function simply becomes u, which is, of course, what we wanted. And dt is equal to du, so we can just substitute du here. Now we have what we desired. We have a delta function with a single parameter as its argument. And so now, as before, the first question we have to ask ourselves is this. We say, is u equals 0 in the range of integration? And it is, because 0 is between -1 and 1. And so, therefore, the value of the integral is simply equal to the integrand with the delta function taken away. It's equal to the integrand evaluated at u equals 0. And so when we evaluate this at u equals 0, we get -2, which is 0 minus 2. So we have -2 to the 5th power, or -32. But note here that if our original integral had been this, if we had been asked to find the integral from -1 to 1 of t to the 5th delta of t plus 2 dt, so that's exactly the same integral as up here, but the limits are a little bit different, well then that would not have been equal to -32. And let's see if we can understand why. So once again, to evaluate this new integral, which by the way is not in your book, to evaluate this new integral, once again, we start by realizing that the argument of the delta function is not just a single simple parameter there. And so we would like for it to be, and therefore we will let u equal t plus 2, and again du is equal to dt. And so once again then, since u is equal to t plus 2, then this t is equal to u minus 2, so we substitute u minus 2 there. Just like we did before, we bring down the exponent of 5, the t plus 2, and the argument of the delta function becomes u, so we have delta of u. The dt is equal to du, so we have du here. But now, since we had different limits on the integral in this case, we're going to get different limits after using this this change of variable. And so let's see what our limits on our integral should be. Okay, again, u is equal to t plus 2. So when t is -1, u will be +1. So the lower limit is +1. And when t is equal to the upper limit, 1, well, u is equal to 1 plus 2, which is 3. So after the change of variable in this integral, we get this expression. And now when we ask ourselves if u equals 0 is in the range of integration, the answer is no. 0 is not between 1 and 3. And therefore, over this entire region of integration, this delta function is always equal to 0, and therefore the integral itself is equal to 0. So this is why it's crucial to check and see if the point at which the argument of the delta function goes to 0 is within your region of integration. If it is not, then the value of the integral is 0, but if it is, then you proceed as we have been doing. Okay. So those are 3 examples with the impulse function. And now let's get to the second part of this lecture, which is the question of energy signals and power signals. So once again now, I will let you look at the material in the book to get some of the background material if you want to look at that. But the basics of how you do problems of this nature, I will show you right now. So we have, let's look at problem 133b, which says that x of t is equal to 3 times u of t plus 2 minus u of t minus 2. Now, it probably is worthwhile to remind ourselves of what this looks like. So actually, let me stop for just a moment and draw a little graph here, and then I'll resume. So we'll just pause for just a moment. So now we have in a graph. You know, the graph is not absolutely necessary in this problem, but it, here we go. A graph is not absolutely necessary, but it probably is nice to give you a little better idea of what's going on. So anyway, in problem 133b, the function that we are considering is 3 times the quantity u of t plus 2 minus u of t minus 2. And so that looks like this. At negative 2, it jumps up to a value of 3 because of this 3 out here. And then it stays equal to 3 until we get to t equals positive 2. And everywhere else outside of that region between negative 2 and 2, the function is equal to 0. And we want to know if this is an energy signal, a power signal, or neither. And so the first thing we do in problems of this type is we ask ourselves, well, is it an energy signal? And so we look at the energy, and the expression, as you see in your book, the expression for the energy is E equals the limit as t goes to infinity of the integral from negative t to t of the magnitude of x of t squared dt. Now, this magnitude is important that you realize what that means. That is the complex magnitude. So it's the function multiplied by its complex conjugate. Now, if it's a real valued function, of course, the complex conjugate is just the function itself. But if it has a complex part, or excuse me, an imaginary part, then you will need to take into account the complex conjugate. Okay, so in this case then, this expression for the energy E will become limit as t goes to infinity of the integral from negative t to t of, well, you see what happens. We have the magnitude of x of t squared dt. Well, that becomes then, we don't have to extend t any beyond we don't have to extend t beyond 2, because once we get to t equals 2, then we have this expression, and if we go any further than t equals 2, then we get out into this region where the function is equal to 0 and it's not contributing to the integral. So this expression right here just becomes the integral from negative 2 to 2, and the value of the function in that region is everywhere just 3. So we just have the integral from negative 2 to 2 of 3 squared, remember we have to square it now, of 3 squared dt. And so, of course, 3 squared is 9, and that's a constant, so it can come outside of the integral. So we have 9 times the integral from negative 2 to 2 of 1 dt. And so E is equal to 9, and when we integrate 1 dt, we get t. And so, and the limits are negative 2 and 2. So we have 9 times the quantity 2 minus the negative 2, or 9 times 4, which is 36. So we have obtained here a finite value for E, as is stated here. And so since E is finite, this is an energy signal. And that's it. We don't have to worry about anything else. Once we have determined that a signal is an energy signal, it can't be anything else, and it can't be both an energy signal and a power signal, so you don't need to check anything else. This is an energy signal, and that's the end of the work for that problem. Now, let's go to another problem. In 135A, we have exactly the same question, but a different function. So here, x of t is equal to the quantity 1 minus e to the negative 2t times u of t. Now the graph of that is over here, and notice that what's going on here, just to make sure it's clear, because of the presence of this u of t, everything is equal to 0 in the region t less than 0. So we only have to worry about what's going on over here where t is greater than 0. And there we have the expression 1 minus e to the negative 2t. Now, at t equals 0, e to the 0 is 1, so we have 1 minus 1, which is 0. So that's why we start out at 0 here. And then as t gets bigger and bigger, e to the minus 2t gets smaller and smaller. And so we asymptotically approach a value of 1. Because this term, as t is getting bigger and bigger, this term gets smaller and smaller. And so we're asymptotically approaching this value of 1. And we want to know if this signal is an energy signal, a power signal, or neither. Now the fact that this function goes on and on without going to 0, that very strongly suggests to you that the energy is not going to be finite in this case. But let's check it and make sure. Okay, so once again, since our goal is to determine whether x of t is an energy signal, a power signal, or neither, the first thing we will do is to check its energy. So as before, the energy is equal to the limit as t goes to infinity of the integral from negative t to t of the magnitude of x of t squared dt. So in this case, that becomes limit as t goes to infinity. Now, because of the presence of that u of t, the lower limit on the integral becomes just plain old 0. The upper limit is capital, it remains as capital T, and then when we substitute in this 1 minus e to the minus 2t for x, we get this. And notice now, we don't have to include u of t. We've already included the effect of u of t by setting the lower limit of the integral to 0. But everywhere in the positive range, u is equal to 1, and 1 squared is equal to 1, so we really don't have to include that. Okay. So now we need to see about evaluating this integral. And, you know, when we square this binomial here, we square the first term, we get 1, multiply the first times the second and double it, so we get minus 2e to the minus 2t. And then finally, when we square the last term, okay, we're going to get e to the minus 4t. And it will become plus here, because we have negative times negative is positive. So we will get this expression. Now, let's go ahead and integrate each one of those terms. When we integrate 1, we get t. When we integrate negative 2e to the negative 2t, that has the form e to the u du when we take into account the dt part. So we just get e to the u, e to the minus 2t. And then finally, for this integrating this last term, we would need to multiply it by negative 4 on the inside of the integral and negative 1/4 on the outside. So here's this negative 1/4, and we would get e to the minus 4t. And again, the limits on the integral are 0 to t. Now, if we evaluate everything here at the upper limit and then subtract what we get when we evaluate everything at the lower limit. Okay, at the upper limit, we get t plus e to the minus 2 capital T minus 1/4 e to the minus 4 capital T. So this is what we get at the upper limit. And then at the lower limit of 0, okay, t is 0, and e to the minus 2 times 0 becomes 1, minus 1/4 of e to the minus 4t becomes minus 1/4 e to the 0, which is minus 1/4 times 1, or minus 1/4. And so this is what we have. And then to gather all these terms together, we get this expression for e. And now if we think about what's happening as t goes to infinity, well, as t goes to infinity, e to the minus 2t goes to 0, and e to the minus 4t goes to 0. 3/4 just, or minus 3/4 just stays as minus 3/4, but as t goes to infinity, this t here is getting bigger and bigger and bigger. So e is not finite in this case, and therefore this x of t is not an energy signal. So the next thing to do then is to say, well, if it's not an energy signal, is it a power signal? And to determine that, we have to look and see if the average power is finite. Now, the formula for the average power is given here. If x of t is a periodic function, all we have to do is to integrate 1 over t naught, where we're assuming t naught is the period here. So all we have to do is integrate x of t squared over 1 period and then divide by the period. And by the way, the limits here are shown as minus t naught over 2 to t naught over 2, but you don't have to use those limits. As long as you integrate over 1 period, it'll be fine. So you could integrate, for instance, from 0 to t naught if you would prefer, instead of integrating from minus t naught over 2 to t naught over 2. But just keep in mind that this, you can do this only when x of t is periodic. If x of t is not periodic, then you have to use this definition for the average power. And so that's the limit as t goes to infinity of 1 over t times the integral from minus t over 2 to t over 2 of the magnitude of x of t squared. And don't get this mixed up. Here we have minus t over 2 and t over 2. And when we're talking about the energy, we have the limits are negative t and t. So don't get that confused. Okay. So in this particular problem that we're looking at, remember this is problem 135a, where we have this function, 1 minus e to the minus 2t times u of t. And clearly you can see from the graph, this is not a periodic function. And therefore, we're going to have to use this second definition for the average power. So, as I say, in this case, x of t is not periodic, and so the average power is given by this formula right here. The limit as t goes to infinity of 1 over t times the integral from negative t over t, times the integral from negative t over 2 to t over 2 of the magnitude of x of t squared dt. Okay. Well, again, as we did before, we can proceed as follows. Now, let me point out, we can use some of our previous work here. Here we were integrating x of t squared from 0 to t. And down here, we want to integrate x of t magnitude squared from minus t over 2 to t over 2. So we can use some of the work from above. We found out that here we obtained, for the integral, we obtained this expression right here. So we're going to obtain that same expression again below, except we have a negative t over 2 and a t over 2 instead of the 0 and t. And remember, we also want to have 1 over t out front here as well. Still inside the limits, but in front of this expression. So let's, we might as well use our previous work and not do that all over. And so that's what we have right here. Okay, and now we will evaluate the term in parentheses at the upper limit to get this, and then subtract what we get at the lower limit, 0, which is this. And so when we write all of this out, we're going to get this. And now let's look at that. Okay, the 1 over t times t over 2 just becomes 1/2. Now e to the minus t over t, as t goes to infinity, e to the minus t is going to 0, and 1 over t is also going to 0. So that goes away. By the same token, e to the minus 2t goes to 0, and the t in the denominator would go to 0. Minus 3/4 doesn't change as t goes to 0, but we do have, again, this t in the denominator, so that's minus 3 over 4t, and so that as well will go to 0. So the only thing that's not going to 0 here is the 1 over t times t over 2, and is equal to 1/2. And therefore, this complete expression is simply equal to 1/2. And 1/2, of course, is a finite number. So we have found out that the average power is finite. So this function is a power signal. And now we want to do one last problem. The last problem for this lecture is still another function. And notice this is very similar here to what we've just done. The only difference is in the problem we just did, it was 1 minus e to the minus 2t. Now this function is 1 minus e to the positive 2t times u of t. And again, we want to know if this is energy signal, a power signal, or neither. Now here is this function. It starts off when t is equal to 0, we have 1 minus 1, so it starts off at 0. But then as t increases, this e to the 2t term here gets bigger and bigger and bigger, and it's getting subtracted from 1, so we get this negative number that's getting larger and larger and larger. Now, whenever you have a case like that, this strongly suggests that not only is this not going to be an energy signal, but this is likely not going to be a power signal either. Now it's because of the rate of increase of this, which is exponential. Now, if this were, and you might say, well, I said increase, this is decrease. Okay, that's fine. But remember, we will be squaring this down here in the integral. But if the rate at which this is increasing or decreasing is not too big, we might still get a power signal. But in this case, it is an exponential decrease. And so therefore, we suspect that this function is not going to be either an energy signal or power signal, but we need to go ahead and do the calculation to make sure. And let me break for just one moment here. Okay, I had to pause there because I just realized I made a mistake. So let me restate something I just said. I said that if this function were increasing or decreasing sufficiently slowly as we went to infinity, it might still be a power signal. That is incorrect. If, as you go to infinity, if the function is increasing or let's be careful here. If the function is increasing in magnitude, okay, if the function is increasing in magnitude as t goes to infinity, even if it's increasing very, very, very slowly, if the function is increasing in magnitude as you go to infinity, it will not be, it will certainly not be an energy signal, but it won't even be a power signal either. So I wanted to correct that statement. And so in this case, obviously this function is increasing in magnitude as we go to infinity, and therefore we could say this will not be a power signal, but I want to work it out for you and make sure you see the math behind it. So again, when you have this kind of problem, the first thing you do is calculate the energy, and so the definition for the energy is given right here. And when we substitute in for x of t, just as before, the presence of this u of t will make the lower limit become 0. And then if we square 1 minus e to the 2t, we would get 1 minus 2e to the 2t plus e to the 4t. And then when we go ahead and do the integral, we will get this. And the limits are 0 and capital T. And so when we evaluate at the upper limit, we get this, and evaluate at the lower limit, and we get this. And then when we subtract, we will be left with this. So we have that the energy is equal to the limit as t goes to infinity of capital T minus e to the 2t plus 1/4 e to the 4t plus 3/4. And that is not finite. And therefore E is not finite, and therefore x of t is not an energy signal. So now we have to calculate the average power. Now, we already looked at the formula for the average power, but remember that formula had two parts, and one part was for the case where x of t is periodic, and one case, the other part was for x of t not periodic, and this function clearly here is not, this function is not periodic, so we have to use that second part of the formula. P average is equal to the limit as t goes to infinity of 1 over t times integral minus t over 2 to t over 2 of x of t magnitude squared dt. Just as before, we can use some of our work in calculating the energy here in calculating the average power, and so we're going to do that. So the way that I jump from here to here is by using this work right up here. But notice that the 0 will become, we have negative t over 2 there, but then again, because of the presence of the u of t, that will be 0 again here. But the upper limit of t now becomes t over 2 in this case, because as we said before, for the average power integral, the upper limit is t over 2 instead of t as it is up here. And then one other difference is we have to remember to put this 1 over capital T here for the in the average power. So this is what we will have when we substitute in for the integral and evaluate the integral. And then when we evaluate at the upper limit, we get this minus the lower limit and we will get this. And therefore, when we simplify all this, we get this term here in brackets. And when we multiply through by 1 over capital T, okay, the T over 2 times 1 over T, we get 1/2 minus e to the T over T plus e to the 2T over 4T plus 3 over 4T. And now as T goes to infinity, this last term will go to 0 because of the T in the denominator. And the first term remains finite. But for the second term and the third term, admittedly, the T in the denominator of both of those terms will tend to make the terms get smaller. But the e to the T in the top, in the numerator, is getting big much more quickly than the denominator is getting big. And therefore, these terms are blowing up. This would go to positive infinity. And in fact, it's going to positive infinity very quickly. This one's going to negative infinity here because of this negative sign, but this is the dominant term. And so overall, this is going to positive infinity. And so it's not finite. So in this case, the P average is not finite either. We've already found that the energy was not finite. In this case, the average power is not finite either. So x of t in this case is neither an energy signal nor a power signal. So that shows these last three problems in this lecture show how to determine if a signal is an energy signal, a power signal, or neither. And so these examples that we've done in this lecture will prepare you for test 4. That concludes this lecture, and good luck.